Hi, and welcome to this short video introducing the Atom Probe facility at MPIE. The Atom Probe facility at MPIE is run around the Atom Probe Group, which contains 6 to 8 PhD students, a dozen postdocs, and 2 technicians full-time and a part-time technician shared with the group of Stefan Zefferer. These are Andreas Sturm and Uwe Tedzins, who manage the FIB and the Atom Probe respectively, and Christian Bros, who also helps with the training on the FIB and is also helping to manage some of the cryo Atom Probe facility. The group is focused on using advanced microscopy to understand nanostructured materials and work across a broad range of materials from metals and alloys for more structural applications on steel and nickel and cobalt superalloys and aluminium. Also, we have a strong focus on hydrogen and hydrides in steel and titanium and zirconium alloys, and this is partly funded through the ERC Shine. And we also have an activity on materials for energy applications, which is quite broad, including magnetic and thermoelectric materials and catalysts, also in parts funded by this ERC grant. The Atom Probe facility at MPIE started with a LEAP 3000 HR and a LEAP 5000 XS, complemented by 2 FEI FIBs based on the gallium beam. And in 2017, there was an addition of a 5000 XR, and a second 5000 XR was added in 2019 to replace the 3000. And in 2017, we also had installed a plasma FIB using xenon instead of gallium. We have a cryo SAM FIB coming in principle in 2022. Some of this infrastructure and instruments are part of the LAPLACE project, so the 5000 XS and XR atom probes, a glove box which is located in room 517, and the plasma FIB. All of these are connected through transfer suitcases and as part of the so-called LAPLACE project. For more details, please feel free to contact me. So just as part of the introduction, what is atom probe tomography? Atom probe tomography is a microscopy and microanalysis technique. It makes use of a very sharp needle-shaped specimen, where at the apex of which, when we apply a high voltage, is generated a high field. The field, when it reaches 10 to the 10 volts per meter roughly, starts to transform these surface atoms into ions, which are accelerated by the field, projected away from the needle, and fly along trajectories that are well determined based on the distribution of the electrostatic potential in the chamber. We collect these onto a detector that is sensitive to the impact position. We time the departure of the ions by using either high voltage pulses that will temporarily increase the amplitude of the electrostatic field, or by using laser pulses that will temporarily increase the temperature of the specimen apex. And this gives us the start of the time of flight measurement, and we can measure the time of flight up until the point where the ion strikes the detector. This gives us a mean to use time of flight mass spectrometry to identify each ion, so we can associate to each ion an elemental identity. The impact position and the order in which we detect the ions can be used to build a 3-dimensional point cloud where each point is one ion that was detected and repositioned in 3 dimensions. So atom probe is primarily a mass spectrometry technique. So we get first a mass spectrum, giving us the quantity of atoms from each isotope that we have inside of the piece of material that we've analyzed. So here, for example, a piece of steel that contains vanadium and chromium. We can see the different isotopes of chromium, manganese, iron. And the relative amplitude of each peak reflects the relative amount of specific atoms of a specific species within the sample that was analyzed. And the second aspect of atom probe, the strength of atom probe, is its high capability to locate atoms in 3 dimensions. So we can see now, for example, in this nanocrystalline aluminium alloy, there's 3 grains that have been analyzed. We can rotate the volume in 3 dimensions. We can look and probe the composition of the particles that we have here, the precipitates that are inside of the grains, and the composition, for example, here of these grain boundaries. We can isolate individual particles to look at their individual composition. And sometimes we actually can find trace of the crystallography of these different grains. So here we can image different sets of atomic planes within the reconstruction. A key strength of MPIE has been the development of infrastructure and methods to complement measurements obtained from transmission electron microscopy. In this case, for example, scanning transmission electron microscopy through an atom probe specimen, in which we can see contrast pertaining to precipitates strengthening this austenitic steel, and we can perform high resolution, high angle annular dark field STEM on these samples. We can image the organization of the atoms here, for example, inside of one of the strengthening precipitates. And the matrix, we can see that the organization of the atoms is different. We could do spectroscopy, for example, but that would only give us some partial information because we have a through thickness integration of the information. And also for light elements, the spectroscopic techniques from inside the TEM may not always yield really accurate results. And when we take this specimen and put it inside of the atom probe, what we get is a 3-dimensional compositional field that we can actually use to complement the information that we gleaned from the TEM. So that's a bit of what we do in the group and how atom probe works, and you should always feel free to contact me if you have any questions or interest in using the technique. Thanks for your attention, and I hope to see you soon.